When I was first taught linear algebra, I learned it was mostly about the sort of stuff you see here: lines, planes, matrices, and linear equations. In this video, I'd like to show you how linear algebra has really important applications for stuff like this: compact disks, QR codes, computer memory, and deep space communication. What ties all of these things together is the need for error correction. CDs get scratched, camera images can be blurry, and electromagnetic interference can corrupt information in electronics, or corrupt signals being sent from space probes back to Earth. In the year 1977, NASA sent out the Voyager 1 and Voyager 2 space probes to study the solar system. Here you're looking at a time-lapse of images Voyager 1 took of the planet Jupiter in 1979. And here is another time-lapse of the planet Saturn in 1980. The Voyager probes had to transmit binary image data hundreds of millions of kilometers across space back to Earth. However, if background electromagnetic radiation is strong enough, it can sometimes turn a 0 into a 1, or turn a 1 into a 0. If left uncorrected, this results in lower image quality, meaning that images like these might not have been possible to capture. This is where error-correcting codes, or ECCs, come in. Error-correcting codes are a way of applying linear algebra and abstract algebra to fix data transmission errors, as in the case of the Voyager probes sending images from space back to Earth. In this video, I'm going to discuss repetition codes, which is the method you would probably use for error correction if you've never studied ECCs before. I'll also talk about Hamming codes, which are a simple trick that can add a significant improvement to the efficiency in the error correction process. The actual error correcting codes used by the Voyager probes are called polynomial codes. Unfortunately, these are too complicated to explain in a single video, but we'll work our way up to an understanding of them over the next 3 to 4 videos. In any case, a lot of the basic ideas behind error correction will still be covered in this video with Hamming codes. And at the end of this video, you should hopefully have a good understanding of how linear algebra is used in technology all around us every day to fix errors. The first type of error correcting code we're going to discuss is repetition codes. This basically just means retransmitting the message multiple times. For example, if we transmit an image of the planet Neptune 3 times, each copy of the image might get corrupted in different ways. But for each individual pixel, we can hope that 2 of the 3 copies of the pixel will be correct. If you're familiar with standard digital images, you'll know that every pixel in a grayscale image is represented by a number between 0, which is pure black, and 255, which is pure white. I'm not sure if this is exactly the image format used by the Voyager probes, but for the purposes of this video, it's good enough. And of course, each of these numerical pixel values can be represented in binary as a long stream of 1s and 0s. So let's take a look at how repeating the image message multiple times can help us fix errors. So we have our 3 copies of the image here, and each one has been corrupted in different ways. Now, if we zoom in on a small region of the image, we find that the pixel values look like this. So you'll notice that the first 2 copies agree with each other, but in the third copy, there's been an error, and that's because in the binary stream of 0s and 1s, one of the 0s got flipped to a 1 due to electromagnetic interference. So let's pretend that we get all this data on Earth. How do we fix the mistake? Well, we can just line up the 3 streams of 0s and 1s and check if the 3 copies agree with each other. So we see that these 1s all agree here, and so do these 1s, and these 0s agree. But here we have a disagreement between the 3 copies. We have 2 0s and a 1. So we're just going to do a majority vote and take the best 2 out of 3 and assume that this should actually be a 0, and that the third copy here contains an error. And just writing out the other answers, we find that we get a result where the error has been corrected. So we've repaired this corrupted pixel. So basically, our procedure for correcting errors is to take the original message and create the repetition code, where each binary digit gets repeated 3 times. Now, as the message travels from the deep space probe back to Earth, some of the binary digits might get flipped. but we can look at each block of 3 bits, and anytime there's a disagreement, we just take the best 2 out of 3. So through this best 2 out of 3 voting procedure, we're able to decode the message and recover the original transmission. Now, it's important to remember that this procedure isn't perfect. Let's go through this process again, but with a different set of corrupted bits. So you'll notice that this time we don't actually recover the original message. There are still errors in the message we decoded. And that's because in some of these 3-bit blocks, there was more than one error. So it's important to remember that the error correction process has limits. If too many errors happen, we simply can't recover the correct data. So with this best 2 out of 3 repetition code that we're using, if more than one error occurs in a 3-bit block, we get the wrong answer. So this means that we can only fix one error for every 3 bits. Moreover, we need to repeat the message 3 times with this method, so that's only a 33% efficiency, because only 33% of the bits we're sending are actually meaningful data. So there's a couple problems with this method. Being able to fix one error out of every 3 bits transmitted is pretty good. This means we can correct a lot of errors. But there might be some situations where we don't need to be this good at correcting errors. For example, maybe we only expect one error out of every 100 transmitted bits. If that's the case, this best 2 out of 3 method is kind of overkill. Another issue is the 33% efficiency. For every 1 bit of real data, we have to add 2 redundancy bits and transmit 3 bits in total. So what if we want better efficiency? Can we get 50% efficiency, or maybe 70%, or maybe even 90%? Well, to deal with both of these issues, I'm going to introduce a new type of error correcting code called Hamming codes. Specifically, I'm going to talk about the Hamming 7.4 code. So the best 2 of 3 repetition code takes a 1-bit message and turns it into a 3-bit code word by repeating it 3 times. So the 0-bit message gets turned into the code word 000, and the 1-bit message gets turned into the code word 111. Now the Hamming 7.4 code takes a message of 4 bits and turns it into a 7-bit code word. So the message 1001 gets turned into the code word 1001001, and the message 0010 gets turned into the code word 0010011. So to communicate a 4-bit message, we need to transmit 7 bits. So that means that the Hamming 7.4 code has an efficiency of 4 over 7, which is 57.1%. And this is a pretty big improvement over the 33% efficiency of the best 2 out of 3 code that we used earlier. So let's take a look at how this Hamming 7.4 code works. Let's say that we have this binary message that we want to transmit using the Hamming 7.4 code. The first step is to divide the message up into 4-bit chunks. Now, for each 4-bit chunk, we're going to add 3 extra redundancy bits, and I'm calling these extra bits X, Y, and Z. So how do we calculate X, Y, and Z? Well, I'm going to call these first 4 bits A, B, C, and D. And the X, Y, Z bits are given by these 3 equations here. This circle plus symbol is called the exclusive OR operator, or the XOR operator. The XOR operator is very similar to ordinary addition, but with a slight difference. In these first 3 cases, the XOR operator behaves exactly like ordinary addition, but for 1 XOR 1, this actually gives us 0 instead of 2. So you can basically think of the XOR operator as a special type of addition where if the answer is even, we get 0, and if the answer is odd, we get 1. So let's compute the XYZ redundancy bits for this 4-bit chunk, 1101. So X equals A XOR B XOR D, so that's 1 plus 1 plus 1, which is equal to 3, which is odd. And since we get an odd answer, we get X equals 1. And Y equals A XOR C XOR D, and that's 1 plus 0 plus 1, which is 2, and that's even. So the answer is even, that means that Y equals 0. And Z equals B XOR C XOR D, which is 1 plus 0 plus 1. And that's 2, which is even, so Z equals 0. So for this 4-bit chunk, the redundancy bits are 1, 0, 0. And we can use this same technique to add the redundancy bits to all the 4-bit chunks in our message. For the X bit, we XOR ABD. For the Y bit, we XOR ACD. And for the Z bit, we XOR BCD. And we can do this on and on for all the 4-bit chunks and get a bunch of 7-bit code words ready for transmission. Now let's see if we can correct some errors. So let's say some 7-bit code word gets transmitted from space and arrives on Earth. And on Earth we receive the bits 0100-101. So let's check these 3 redundancy bits here and see if they agree with these equations. So X is the XOR of ABD, which is 1, so the X bit makes sense. Y is the XOR of ACD, which is 0, so the Y bit makes sense. And Z is the XOR of BCD, which is 1, so the Z bit makes sense. So the redundancy bits are consistent with the data bits. And while that doesn't prove that no errors happened, it does indicate that the bits are probably correct, provided too many errors didn't happen. Now let's look at another example where the received bits are 1001, 010. So again, we'll check the redundancy bits against these 3 equations. So looking at X, we get 0, looking at Y, we get 0, and looking at Z, we get 1. So these redundancy bits are not what we expect, so that means that we have errors. So how can we correct this message? Well, since the Y and Z bits are incorrect, let's take a look at the Y and Z equations here. Now, we notice that these equations contain both the C bit and the D bit. So that's an indication that either the C bit or the D bit are probably wrong. But notice that the X equation also has the D bit, and the X bit was fine. So that indicates that the D bit was probably right. So by the process of elimination, we can conclude that the C bit was probably flipped. So if we change this C bit from a 0 to a 1 and check the X, Y, Z bits again, we find that they all check out correctly. So using these 3 extra redundancy bits, we were able to correct a 1-bit error in this 7-bit chunk. So let's just review the whole process of using the Hamming 7.4 code. We break our message up into 4-bit chunks. We add 3 redundancy bits to each chunk according to these equations. Then we transmit the message, where noise can possibly flip some bits and give us errors. Then we check the 3 redundancy bits against these equations to detect and fix errors. So here, only the X bit is wrong, which indicates the error was probably the X bit. Here, the X, Y, and Z bits are all wrong, and since the D bit is in all of these 3 equations for X, Y, and Z, that indicates that the D bit is probably the one that was wrong, so we can flip the D bit to fix the mistake. And in this case, the X, Y, and Z bits are wrong again. This would normally make us think that the D bit is wrong. However, flipping the D bit doesn't actually give us the original message, and that's because there were 2 errors in this 7-bit chunk, which is too many errors. The Hamming 7.4 code can only correct 1 error in every 7-bit chunk. So now we've covered the best 2 out of 3 repetition code and the Hamming 7.4 code. The 2 out of 3 code has a data transmission efficiency of 33%, and we can do 1 correction per 3 bits. The Hamming 7.4 code has a transmission efficiency of 57.1%, and we can do 1 correction per 7 bits. Even though we can't correct as many bits using the Hamming 7.4 code, it has a significantly better efficiency, so we can send the same message using fewer bits. And, correcting 1 out of 7 bits is still pretty good, and in a lot of cases this will work out just fine. Now, I've described the basic mechanics of the Hamming 7.4 code, but at this point it probably just seems like a set of magical equations that someone invented while playing around with bits. There's no real indication of how it was invented or why it works the way it does. I'm going to finish this video by explaining where these formulas come from. So if we look at this 7-bit chunk here, the stars of the show are really these XYZ bits. These XYZ bits are what help us detect whether or not an error has occurred. And with these 3 check bits, we have a total of 8 different possible combinations of zeros and ones. That basically means these 3 XYZ bits have the ability to communicate to us one of 8 possible states. So if we can detect 8 possible states, what should those states be? I'll show you the 8 states that we'd like to detect here. So this first state here, we see that we have 7 check marks, and this indicates a state where all 7 bits, A, B, C, D, X, Y, Z, are all correct. So this is the state where all 7 bits were transmitted correctly and there were no errors. With this state over here, we see that all bits are correct except for the first one, which is the A bit. So this is the state where the A bit has an error and has been flipped. This is the state where the B bit has an error, and this is C error, D error, X error, Y error, and Z error. So the fact that these 3 error check bits can indicate 8 possible states is very useful. It gives us 1 state for the no error case, and 7 states for the 7 possible 1-bit errors that we might see. This is why the Hamming 7.4 code can only correct 1 error per 7-bit chunk. The 3 error check bits only give us enough states for these 8 cases. If we wanted to correct cases with 2-bit errors, we would need more check bits so that we could represent more error states. Now, I've written these 3 check bits in the form of zeros and ones, but that's not the best way to think about them. Recall that when we're looking for errors, what we're really doing is checking whether or not these 3 XYZ bits are consistent with the other bits. In this case, X, Y, and Z should all be 0, so that means that the Y bit is consistent, and these X and Z bits are not consistent. So it's better to think of the check bits in terms of these correct and incorrect indicators, the check marks and the X's, instead of the plain zeros and ones. So on the left here are the XYZ check bit states that we can calculate with some equations. These check bit states are also sometimes called syndromes. And on the right, we have the actual error states, and these basically give us instructions for correcting the errors if there are any. So what we need to do is somehow connect the check bit states with the error states. Given a check bit state, we need to know what error state we're in so that we can correct the error. So I've written out all the 8 check bit states here, and we need to decide which error state they will represent. So if all the check bits are correct, it makes sense that this represents a state with no errors. So all of the ABC XYZ bits are correct. Now these next 3 states are the cases where the X check bit is wrong, the Y check bit is wrong, and the Z check bit is wrong. And so it makes sense to associate these with the error states where the X, Y, and Z bits are wrong, respectively. Finally, there are these 4 check bit states here. So these need to cover the 4 remaining error states for A, B, C, and D. But there's no single correct way to make the association between these check bit states and the remaining error states. So I'm going to do the simplest thing and just write A, B, C, D in order here. So this check bit state will represent the A bit being wrong, and so on and so forth. Now there's no reason I chose this particular order of error states. I could have just as easily picked a different order, like C, D, B, A if I wanted, but since any ordering works, I'm just going to use A, B, C, D. So let's take a closer look at these 4 states with the A, B, C, D bits. So just as a reminder, our goal is to invent some equations for the X, Y, and Z bits, such that when we observe these check bit states, they will correspond to these error states over here. So this is the check bit state for the A bit being wrong, this is the check bit state for the B bit being wrong, and these are the check bit states for the C and D bits being wrong. So reading this table, if any of the A, B, or D bits have errors in them, it should affect the X bit. So we can write this equation here. Basically, we pre-compute the X bit up front before we send the message, and then after we transmit the message, if any of the A, B, or D bits get corrupted, there will be an inconsistency in the value of the X bit. So when the X bit is incorrect, that tells us that we could be in one of these 3 possible states where the A, B, or D bit is incorrect. Since the C bit is not in this equation, the X bit being incorrect will not tell us anything about C. Likewise, from this table we can see that the Y bit should be affected by A, C, and D, so we can write this equation here. And the Z bit should be affected by B, C, and D, so we can write this equation here. So again, we pre-compute X, Y, Z according to these equations, and after transmitting the message, say if the A bit gets flipped, since A is present in the X and Y equations, the X and Y check bits will be incorrect, but the Z check bit will be fine, since it isn't calculated with the A bit. And this gives us the following check bit state, which, as we can see, matches up with the error state of A being wrong. So as we can see, these three check bit equations come from this association between check bit states and error states. And again, there's nothing special about this particular association between the check bit states and the error states. We could have just as easily changed things up, and this would have given us different equations. But the equations I'm showing you now are the standard Hamming 7.4 code equations. So with the Hamming 7.4 code, the numbers 7 and 4 are no accident. If we have 7 bits where 4 bits are the original message, that leaves 3 bits for the check bits. 3 binary check bits will give us 2 to the power of 3 possible check bit states, which means 8 total check bit states. And this matches up with 1 error state for each of the 7 bits, plus 1 extra state where there are no errors and everything is fine. So hopefully this video has given you a good introduction to error correction. The naive method of error correction is just repeating the message multiple times, but that's not very efficient. We've seen how the Hamming 7.4 code adds redundant information in the form of 3 check bits, and these 3 check bits can point us to one of 8 possible error states, which tell us how to correct errors in our message. And this clever trick gives us a better data transmission efficiency rate with the ability to correct errors. In the next video in this series, I'm going to show you how linear algebra can give these linear equations geometrical meaning, and also discuss other Hamming codes such as the Hamming 1511 code and the Hamming 3126 code. And in a later video, I'll discuss the actual polynomial codes used by the Voyager space probes.